In this video, we will be talking about the Gauss-Jordan method, and the Gauss-Jordan method will involve a 3 by 4 augmented matrix. So, as we made mention last in previous videos, you have to have a row leading 1 in the diagonals, and that this is your coefficient matrix. And this is your solution size basically. So you want to get a 1 in this position, a 0 in this position, a 0 in this position, a 0 in this position, a 1 in this position, a 1 in this position, a 0 in this position, and a 0 in this position, and a 0 in this position. So it's going to take some sort of a regimen of order, mainly a pattern. You want to go into a pattern, and as you're solving a matrices or as you're using this method, you want to go into some sort of pattern. Now, there's different patterns. You can start here at this point and actually work your way down, getting a 1 here, and then getting a 0 here, and then getting a 0 here. Now, sometimes you can continue around or go straight to the middle here to get your 1 there. Then getting a 0 here, and getting a 1 here, and getting a 0 here, getting a 0 here, right? And then getting a 0 here, right? So each time you're doing something, you're writing out an algorithm to 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 get these numbers to these positions. However, so it's going to take some mathematics and some arithmetic organization as you are solving this step by step. Now that's one pattern, right? So let's look at another pattern basically. There's different patterns. So supposing you start here, we'll always start here at this position. This could be like a 4. If this was a 4 here, you can actually, divide row 1 by 4 to get a 1 here. 4 divided by 4 is 1. But you got to remember, you got to divide 4 to the other numbers involving this row as well, right? So as you go down to get these positions to where you like, you can also, as we did before, we went straight here, but now we can keep going around to get a 0 here, to get a 0 here, right? To get a 0 here. Now, sometimes people go right straight here and get a 1 here, and then go back out to get a 0 here and to get a 0 here. That's another type of pattern, right? That's another pattern. I didn't want to do that. I don't know why I cleared the whole thing. Let's see, let's go back and put this up here again. Didn't want to clear that whole thing out. Hang on. I want to show you another pattern. Oops. A, B, C. Okay. So we start at the 1. We'll start here at this position to get a 1 there. And we go down to get our zeros here as appropriately. We go around here to get our zeros here. And we get a 1 right here. And sometimes we go straight here and then go back out to get a 0 here. And then go up to get a 0 here and a 0 here. Okay? That's another type of pattern. Or another pattern, if you will. Let's see if there's any more patterns that we can do. Basically, that's basically it for the patterns. And the reason why I say go just stick strictly to the pattern so you won't be jumping from one extreme to another trying to get zeros and ones where they belong. Then once you get zeros and ones to where they belong and you're going from one extreme to another, you'll have another value pop up in there and you won't never get to the solution or get to the identity matrix that you need to find these particular solutions. So there's warnings, and with experience, this will help you more as you do more of these problems. As you do more of these problems, you'll get much better. You'll get better at all of these problems, solving these problems, and using these methods. So it takes some practice. It takes some uh, involvement with actually working these problems in order to be successful with them every time. So let's do an example. Let's do an example. Okay, and say we're gonna pick a systems of equation and convert it. So x minus 2y plus 3z is equal to 9 minus x plus 3y equals negative 4. Let's say negative 4. And then this will be 2x minus 5y plus 5z is equal to 17. So our matrix is going to look like this, 3 by 4, which is 1, negative 2, 3, this will be 9, this will be negative 1, 3, 0, negative 4, and this will be 2, negative 5, 5, 17. Okay, so this is the 3 by 4 matrix that we'll be working with. So let's first thing is first, right? So we have a 1 in this position here, so we don't have to do anything with this. So the next thing we can actually do is that we can actually take and make a 0 in this position. We want a 0 in this position. So a 0 in this position, so how do we do that? So we take row 1, add it to row 2 to get the new row 2. Let us show our work with that. So this will be 1, negative 2, 3, and 9. This will be negative 1, 3, 0, negative 4. So this will be 0, 1, 3, and this will be 5. So what do we do next? Basically what we do next, we have our new row 2, so we'll write our matrix like we want it, which row 1 and row 3 will stay the same. The only thing will change is row 2. So we see that. Okay? So the next thing we'll do, what we'll do is actually we will get a what here? A 0 in this position. So we'll get a 0 in this position. How we do that? We're going to say negative 2 to row 1, add it to row 3 to get the new row 3. And so we'll say negative 2, This will be 1, -2, 3, and this will be 5. So this will be -2, +4, -6, and then we have -18. Did we make a slight error somewhere? Okay, I think we did. So this should be a 9 right here, folks. So let's go back. See, the reason why I write these things out, particularly, is if I make a mistake, see, we can find a mistake very, very easily. And I was able to catch myself. And so here, this is a 9. That's why. That's why when we actually distribute this here and distribute this here and distribute the -2 to this number and distribute this now here, we get these numbers, -18. Okay, great. So so now we have to add row 3 to this. Row 3, so this will be 2, -5, 5, and 17. So this will be 0, -1, -1, and this is also -1. We see that. So we have our row 3 established for now. So make sure you got these notes copied down in good detail, right? And so we'll erase the board and continue with our problem. So here's our matrix. Here's our matrix. Oops. And this will be 1, -2, 3. This will be 9. This will be 0, 1, 3, 5. And then this again will be 0, -1, -1. And this will be also -1. So now, since we already have, the blessing here is that we already have a 1 there. So we don't have to go to the middle for this pattern. We can still go right around here. We went here, here. Now we're going to here. We don't have to go here. Why? Because it's already a row leading 1 there. So we don't have to do anything with that. But we want to get a 0 here in this position. So all we have to do here for this particular problem is to add row 2 plus row 3 to get the new row 3. So in this case, 0, 1, 3, 5, and this will be 0, -1, -1, and -1 here. So this will be 0, 0, 2, and this will be 4. So writing this matrix out, we have 1, -2, 3. This will be 9. This will be 0, 1, 3, and this is 5. And this is going to be 0, 0, 2, and this is going to be 4. Okay, so now we want a 1 in this position. So what do we write? We say row 3 divided by 2 to get the new row 3. And sometimes another way of writing this, you can say 1/2 times row 3 to get the new row 3. Okay, so this here is going to be 0 over 2, 0 over 2, 2 over 2, and then 4 over what? 2. So this is our new row 3, 0, 0, 1, and this will be 2. Look at that. Okay, very good. So writing out the matrix, writing out the new matrix for this algorithm, we have 1, -2, 3, this will be 9, okay, this is going to be 0, 1, 3, 5, this is also going to be 0, 0, and 1, and this is going to be 2. Everybody following me? This is already in reduced echelon form, but we want to go all the way to, I'm sorry, this is already in row echelon form, row echelon form. This is in row echelon form. So we want to go to reduced row echelon form. So we got to keep going because we got to get zeros now. We have zeros in the bottom diagonal, but we're not done. We need zeros in the top of the diagonals, right? And actually, you can continue on to solve this, but that's not the method that we're doing. We're showing you a different method, which is the Gauss-Jordan. So now we have to get the zeros in this position, this position, this position. So with that, we want to get a 0. We want to get a 0 here. We want to get a 0 here. So what we want to do is say -3 to row -3 to row 3 added to row 2 to get the new row 2. So when we do that, this will be -3. This will be 0, 0, 1, 2. This is going to be 0, 0, -3, -6. So this will be 0, 1, 3, and then 5. So this will be 0, 1, 0, -1. So we have a -1 for there. So write this matrix again. What do we have? We have 1, -2, 3, this would be 9, 0, 1, 0, -1. This will be 0, 0, 1, and 2. You see that? So continuing on, where are we going to go to next? We can get a 0 at this position, or we can get a 0 here. So we want to get a 0 in this position here. So what do? We'll say -3 to row 3, add it to row 1 to get the new row 1. So we'll say-3. This will be 0, 0, 1, 2. This will be 0, 0, -3, and -6. And that's going to be added to row 1, which is 1, -2, 3, and this will be what? Oops. Make sure this is neat. Okay, so that's 9. This will be 1, -2, 0, and this is also what? This is going to be 3. So that's our new row 1 for now. Make sure you pause the video to write this down. We're going to clear the board so that we can go to continuing the problem. So writing out the matrix, 1, -2, 0, 3, and it's going to be 0, 1, 0, -1, and this is going to be 0, 0, 1, and 2. So what do we want to do now? Finally, we want to get a 0 in this position here. So we're going to multiply 2 to row 2, add it to row 1 to get the new row 1. Let's write that a little bit better. Let's write that over here. So row 2 multiplied by 2 plus row 1 added to row 1 to get the new row 1. So this will be 2 times 0, 1, 0, -1. So that'll be 0, 2, 0, -2. And so we're going to add that to row 1 again. 1, -2, 0. And this is going to be what? 3. So that's going to be 1, 0, 0. And that's going to be 1. So actually our final answer, let's look at our matrix first. In reduce row echelon form, so we have our identity, as you see. This is going to be 1, -1, and 2. So what is our answer? Our answer is x is equal to 1, y is equal to 2, -1, and z is equal to 2. So our ordered pair, well, our solution here in 3D, x, y, and z will be 1, -1, and 2. See? Everybody see that? So if we were actually, this is our solution, this is our answer. But let's just run a check, y'all. Let's run a check. So our original equation So our original equation was this, right? X minus 2y plus 3z is equal to 9. And negative x plus 3y is equal to negative 4. Then we had 2x minus 5y plus 5z is equal to 17. Now what we're going to do, here was our solution. Our solution was what? Solution was 1, negative 1, and 2. When we substitute these back into x, y, and z, we should be getting these values. And if it doesn't, then we know that we're incorrect somewhere. Sometimes you'll have situations where if you don't check all three, it might work for maybe one or two, but you make sure that you run the check for all three equations, or all four, or all five equations, five unknowns. It depends on what type of system that you have, right, and how many equations. You have to run the solutions that you found in every single equation to make sure that it's correct. Because sometimes one or two or three even on a 5 by 5 might be correct, but if you keep going and then you run it in the fourth equation or fifth equation, this solution is wrong. You won't come up with the same thing. So it's important that you run it for everything. So 1 minus 2 times negative 1 plus 3 times 2, what is that going to give you? Well, 1 plus 2 plus 6 is going to equal to what? 9. So that means that that's correct. This is correct here. And then if we do this one here, this one, we have negative what? Negative 1 plus 3 times negative 1, right? Which is equal to negative 1, right? Minus 3, and what do we get? Negative 4. So that's proven to be correct. So do we leave it as it is? Oh, we know that this answer is correct. Let's just continue. Let's just, pack it up and go home. No, no, no. You have to test this equation too because you never know. But just to be sure, you say 2 times 1 minus 5 times negative 1 plus 5 times 2 is going to give us 2 plus 5 plus 10, right? 2 plus 5 is 7, plus 10 is equal to what? 17. So we see that that's right. So we know that this solution for this system is absolutely, undisputably correct.